How are you? So, what's up? Shall we get down to business? Alright, let's check out the last part of the hydrolysis. This time we'll do it a bit theoretically, where we will try to deduce the pH of a salt that comes from a weak acid and also from a weak base. As you well know, hydrolysis is the reaction of the ions that remain in solution after adding a salt. Well, in this case, the salt I am going to show you is ammonium acetate. Methyl group Co, which would be the base, the anion, and now the ammonium NH4. We'll put it in aqueous solution. This is the salt. And therefore, by putting it in aqueous solution, will this salt be completely dissociated? Completely dissociated, as you know, implies on one side I will have the acetate ions, and on the other side the ammonium ions. The still and high ion will be CH3, COO minus, in aqueous solution, the ions, acetate, and on the other hand, the ammonium ions, NH4, plus also the aqueous solution, ammonium. Okay, these are the scripts. In principle, the salt should be neutral, a neutral pH, until we see the potential reactions of the acetates, and ammonium with water, which is an amphoter and therefore could act either as an acid or a base, is an amphoter. If acetate reacts with water, let's write down the reaction CH3. Here we have the acetate. This would be the base. Then the water, the liquid water, would be the acid. From here to here, protons, I would move from the water to the acetate and stay to the right. Weak acid, here you have it, the weak acid, which is acetic acid, CH3COO, also in aqueous solution. This is the acid. Let's give it 1, and 1 has been conjugate bases. Of course, to water, when we have removed the proton, I am left with the hydroxide ions, also in aqueous solution. This would be acid number 2, and this is the conjugate base number 2. Well, because of this acetate, yes, it reacts with water to form some acetic acid. We are introducing into this water a greater amount of hydroxides. And if we increase the amount of hydroxides, what happens to the pH? The pH goes up, the pH will be higher, which is 7, and would therefore have
basic
a pH. This balance is a hydrolysis balance, and I'm going to call it hydrolysis constant number 1. This is the first hydrolysis, the first
action, hydrolysis.
Now, this is the first reaction of acetate with water. If the second script doesn't react with water, it's clear to me, it's a basic pH. But in this case, the ammonia will react well with water. We put the reaction, the second hydrolysis reaction of ammonia, ammonium ion in aqueous solution. This would be the acid. Let's call it acid 1. We put
of water, liquid water.
This would be the base. Let's call it base number 2. And here we put a hydrolysis, a hybrid. If this is the acid, we transfer a proton from the acid to the base. And here I'm left with the conjugate base from the ammonium, which is NH3. Also, in solution to think, if this one I've called acid 1, which is the acid, I have in solution the ammonium. By losing the proton, it becomes its conjugate base, which I will call base number 1. Of course, is this proton has moved to the water, and I'll have 3 or more. Therefore, I will have, because of the ammonium ion reaction with the water base, I will have as the conjugate acid, acid number 2, the dissolution of protons that cause a pH less than 7, or in other words, an acidic pH. Then I have 2 hydrolysis, equilibrium. This is also the second hydrolysis. I'm going to call it K sub H number 2. And I have 2 opposing options. These opposites on one hand Because of this acetate base, we are increasing the amount of hydroxides. And on the other hand, because of ammonia, we are increasing the number of squads. So, who's going to beat me? Whoever wins takes the cat to the water. Then, it depends on which equilibrium wins, or this equilibrium or the constant. Whoever has the higher hydrolysis constant, then it wins. Therefore, yes, the hydrolysis constant number 1 this one right here. What causes hydroxides is greater than the hydrolysis constant number 2. So, and now what would the pH be? It will be greater than 7. So, it's an alkaline pH. Basic. The same if the opposite happens. If number 2 wins, if the hydrolysis constant number 2.
And the one of ammonium.
If this one wins, if it beats the hydrolysis constant number 1, then the pH will be less than 7 and I'll have a pH acid. Then I have to check the two hydrolysis constants. Sure. How could I calculate the hydrolysis constant? How do you calculate the hydrolysis constant? The hydrolysis constant, and we have agreed that it is the one, notice that it is the one. Is the one of this base. And therefore, I'm going to need the acidity constant of this acid. We've seen it in a previous video. Then, to calculate the first hydrolysis constant, I will, the product, let's put a 1 here, the ionic product of water,
Turned green
the constant.
from acidity.
To calculate the hydrolysis constant number 2, we'll need to calculate the hydrolysis constant of 2.
Anyway.
Ionic product of water, here I am, but now I need the ammonia basicity constant. And why do I want this? Well, I could calculate the constant and see who wins, but without needing to calculate it, I can see from the data who's going to win. If I assume that hydrolysis constant 1 is greater than 2, implies that the water's diionic product divided the acidity constant must be greater than the ionic product of water divided by the basicity constant. Let's forget about the ionic product of water, and if 1 over the acidity constant must be greater than 1 over the basicity constant. If we flip it, the acidity constant must be lower than the basicity constant. If that happens, I've got it clear. Yeah? So basic pH doing the same if the acidity constant is greater than the basicity constant. There's no need to do anything in that case.
The pH is, or
What's 7? It's a way to quickly look in the hypothetical case where you have the most complicated case. It would be a hydrolysis of the 2 ions in the salt. Well, this is the theory. Let's get to the problem. Come on, let's get to it.